Is going to be talking with Brian about turning steel.
That's right.
With some very heavy cuts.
Yep, and then we'll go right across the aisle right here to the big boy, the VF3YT50 taper, and we'll bring John Nelson back, and we've got a great cutting demo here.
That's right, and the focus today is not some pretty demo. It's getting heavy cuts done in steel in 3 different applications.
That's right, and throughout the demos, we're going to go to HaasTooling.com. We're going to show you exactly what tools we're using. We're going to show you the feeds and speeds, and Bob and John both are going to talk about how they came up with the feeds and speeds that they're using.
That's right. I'll be over here on the monitor pulling up the different web pages as they pertain. We've also got a PowerPoint that kind of speaks to the different stuff that John and Bob are going to be talking about. And of course, we're also going to have Marcus joining us in the chat, answering all your questions.
Yep, Marcus is
like
on
he always
now.
does, killing it.
Yeah. Okay,
so I think
you want to get started?
I think that's kind of it. So
you're going
over there. I'm going to head here.
I'm going to come over to see Mr. John Nelson. So if you haven't watched before, this is John Nelson, our Senior Applications Engineer. Any of you have watched any demo days? I think you've been in every single one of them.
Yeah. How a UMC is built, I wasn't in.
Yeah, you missed one.
Yeah.
Okay, so you've been with Haas for about 20 years.
Yeah, next month, 20 years.
Okay, and 12 of those, is that what you said, were in an applications role?
Yeah, for 12 years I was either an applications engineer or managing that applications department.
And how many times have you heard people say, Haas can't cut steel? And yes, that's how you all sound in my head.
Yeah, we have definitely heard that before. As the applications department is the group that's responsible for helping Haas customers use their machines. And there are a lot of people who have contacted us about having trouble cutting steel on their Haas machine, but it's not because the machine wouldn't cut steel, it's because they were not running at the correct parameters for that machine, right? You've got, there's a mini mill that's a 7.5 horsepower spindle versus this VF2YT that's got a 30 horsepower spindle.
Right.
So there's a big difference, right? This has 3 times the torque that machine has. You can't take the same cut in steel on this machine as you can on a mini mill. It's that simple.
And then the last demo of the day, we're actually on a 60 horsepower machine.
Yeah.
So even a step up from here. And we were talking a couple weeks ago, there was an application, there was a customer that had a 3 or 4 inch shell mill on a tool room mill trying to take a massive cut, and he couldn't figure out why the machine wouldn't do it.
Yeah.
And that's exactly what you talked about. You got to have the right machine for the job.
Exactly. We get a lot of complaints about cutting aluminum, that another aluminum demo from Haas, or people saying it at trade shows. But there's a bunch of reasons why we actually cut a lot of aluminum. A demonstration is really kind of like a television commercial. You got a limited amount of time to grab somebody's attention, and aluminum demos are impressive. The spindle speeds are high, the feed rates are fast, the chips are flying all over the place. Aluminum demos are interesting to watch. That doesn't mean the machine can't cut steel because we're showing aluminum, obviously.
And there's another good reason for it too, and that's the amount of times you need to change your tools.
Yeah, absolutely. At a 8-day trade show or something, you go through a lot of tooling cutting steel on a demo, because in the Haas booth, we cut all the time. Yep. We're always cutting parts. When the operator finishes a part, they put another one in. There's no sitting there waiting for it or shadow cutting. We don't do that very often at all.
Right. So, okay, we've talked about we can cut steel. We're about to show people to cut steel. One of the things, we talk about horsepower, and you and I just talked about it, but one of the things that comes into play when cutting steel is torque.
Yeah.
And we're going to talk about that a little bit today.
The most important thing is for somebody, if you're having trouble cutting steel, is to understand what model of machine you have, what spindle that machine has in it, and what the torque and horsepower capabilities of that machine, of that spindle, are. Right. We have torque charts displayed on every machine model on our website. They're very easy to see. Andrew's got
I've got it pulled up here, actually, if you want to take a look at it, Frank. So we got the VF2YT here, same machine that you guys have got over there. And so if I, here on the website, if I just page down a little bit, and I go down here kind of to the right, I can see that I have this torque chart. I can just click on that, and there we go. So actually, I'm going to just bring up this version here because it's a little blown up. Same chart. So here's the torque chart for this particular spindle on this machine.
Yeah, you'll see along the bottom is the RPM. So this is the first thing that you need to find on that torque chart. What RPM are you running at? The blue line here is horsepower. And you can see that at very low RPMs, there's not much horsepower at all, because it doesn't take a lot of power to get the spindle turning at 500 or 1,000 RPM. But what it does take is a lot of torque. So we can take that power that we're not using to make the spindle rotate quickly and turn that into torque. So we have maximum torque at low RPM, and that's the dotted line up here. So you can see that our maximum torque on this particular machine is right about 90 foot-pounds of torque. So the foot-pounds are listed on the left-hand side of the chart. The horsepower values are listed down the right side, and along the bottom is RPM. So you find your RPM and then see what torque and horsepower you have at that speed. Don't forget to verify the machine models and the spindle type at the top of this torque chart. On the torque chart for this particular machine, you've got the first chart you're going to see is, I guess, in imperial units, right, using horsepower and torque in foot-pounds. But if you scroll down one, you'll get the, I guess, metric version, where we have the horsepower in kilowatts, actually, the power in kilowatts, and the torque measured in Newton meters. Right. So that's the difference between those. And if you go down again, you'll see the torque chart for this machine with a gearbox. So we have four sets of torque and horsepower lines on this. One of them is the low gear values. The other set is the high gear values, and you can see where the shift point is there. So that's torque chart.
And if you're really doing heavy cutting, you may want to consider doing a gearbox machine, because you can see you've more than doubled your torque at low RPM.
Yeah. So this machine without the gearbox is 90 foot-pounds of torque peak, and then this machine is 250 foot-pounds of torque. So there's quite a bit more. If you're cutting hardened materials, if you're cutting tough materials, stainless steels, titanium, you definitely want to get a gearbox machine. It doesn't mean that you can't cut those materials if you don't have a gearbox. It's just that you can't cut them as efficiently as if you had a gearbox. And we will get back to, after our demonstration, we're going to measure the spindle load values of each of the cutters in our demonstration, and then we'll go back to the torque chart and show you how those values relate to the torque and horsepower curves in the torque chart.
Okay, the other thing we're going to do is we're going to go through each tool. Now, each of these tools is from HaasTooling.com.
Yes.
So we're going to talk about feeds and speeds. Andrew, do you mind pulling up the HaasTooling.com?
Yeah, okay, so from the website, if I go over to the right side of the screen here and I hover over Haas Tooling, this gives you access to all the various menus for the different kinds of tooling that we sell. I've already clicked on the milling section here, and I can see I've got milling bodies, inserts, end mills, all that sort of stuff. I've got another tab open. Here's milling inserts, and this is going to get us close to where you're starting off with, right, John?
Yes. So tool number one in my demonstration program is the 3-inch face mill. It's got the 45-degree inserts here. It's a 6-flute face mill, and we've got the speed and feed chart up there, and I've put a red box around the different parameters that I'm using in this demonstration. You can see I'm cutting an alloy steel over here on the left. I'm using the HMP 35 inserts, which are the preferred grade for steel. And I've programmed it at 850 surface feet, which is right in the middle for a spindle speed. And the feed per tooth feed rate is 10 thousandths, actually just a hair under 10 thousandths, which again is right in the middle of the recommendation. So the point is to show you that if you get these tools from HaasTooling.com, plug in the numbers, if you got all the parameters right, you're going to be right in the ballpark. You'll be able to make those cuts, assuming you've got the amount of torque that's required for that cut. You'll be able to take that cut and then optimize for your particular application if you need to speed up or slow down.
So Andrew, you want to show them how you get to those?
Yeah, so let's go. I'm back now on the main milling inserts page, and I don't have your exact one here pulled up, but let me just click on any one of these because this will just show us. So I click on the insert. Takes a moment.
Of course,
Maybe I should have had that opened already. There we go.
Perfectly yesterday.
So here's in the insert page, and down here you can see technical specs and stuff like that. But what I want is the speed and feed. It's kind of hidden away here. But if I click on this, this will bring us to the same chart that John was just showing, except that John's version that I have here is highlighted, of course. I'm just going to click back over to that. He's got the actual values that he's using highlighted, but you can see it's just a couple clicks away to get the information that you need.
Okay.
So back to you, John.
Yep.
So the second tool in this program is the 3/4 inch 4-flute end mill. This is the standard length end mill, 4 flutes, and Andrew's got it pulled up over there. The surface footage that I programmed is 575 surface feet and 4 thou and 4/10 feed per tooth. On the depth of cut, we're going nice and deep at 1.5 times diameter, and I'll talk a little bit more about that when the actual tool is running. The third tool in my program is the drill. This is an 1.25 inch inserted drill. We're using TSC on this one. Again, we programmed that right at 540 surface feet per minute and feeding at 6 thou and 1/10 feed per revolution on that tool. The last tool is the chamfer tool. I've got the 2-flute 45-degree chamfer tool here. This one's programmed at 800 surface feet, quite a bit faster. It's taking a much smaller cut, and we've got 7.5 thousandths feed per tooth for those 2 tooth, and that's just to put a 50 thousandths chamfer on all the sharp edges on this demo program.
And actually, you just did a video on chamfer mills. We just released that on
Yeah.
YouTube. So if you haven't seen it, check it out. Okay, are we ready for the demo?
I think we are.
Tyler, you want to come in and we'll get you in here tight? So we're going to have Tyler come in and get a close-up, and then we've got a camera inside the machine.
I'll mention one thing real quick. In the demo program, I used a little macro statement to zero out the spindle load meters for each tool before they run, and then it'll record the maximum spindle load that tool achieved during the cut. I've got all of that information being deprinted to a file, and we can take a quick look at that at the end of the demo, and then we'll relate that spindle load information to the torque chart next.
Perfect.
All right?
Okay.
So this cutter's coming in. It's taken 150 thousandths depth of cut and a 2-inch width of cut. My spindle load meter is hovering around 130. You can see the chips coming off there are nice straw colored, and as they hit in the pan, they turn a little bit blue. That means we're cutting just perfectly. Here's the end mill. So this is a 1.5 times diameter deep. This is 1 inch, 125 deep. And I'm taking a 33% of the diameter width of cut, which is 250 thousandths on that 3/4 inch end mill. So 1 inch, 125 deep, and 250 width of cut. We'll take a couple of cuts. And again, you can see that the chips are coming off straw colored or a little bit blue, and when they hit the pan they turn real blue. That means all the heat in the cut is coming out in the chip. This thing's cutting really well.
And what kind of spindle loads do we have?
Spindle load is 75%.
Okay, so you've got some room if you want to.
I've definitely got
push it
room
a
to
little bit.
optimize. I could increase my width of cut and take a bigger spindle load because I've got the headroom there. Do a little cleanup pass here just to
make it look nice.
I was wondering if you could get a shot of the chips over there on the way cover. I'll feed hold this. You can see the color of the chips, how they're nice and blue. The thinner chips, which didn't carry as much heat out, are straw colored, and then the bigger, thicker chips have turned blue because all the heat in the cut has come out in that chip and not in the workpiece or the material. Okay, I'm going to focus back on our part and I'll continue. So that's an 1¼ inch inserted drill going through 3 inches of material. My spindle load is 95%. It's fluctuating a tiny bit right around there, but that's perfect. Right at 100%, 110%, 120%. We can do that all day long with that tool.
And you definitely want through spindle coolant with this
Yes.
tool. You got to get those chips out of there.
Yeah, definitely. Unless you're doing a very shallow hole, you've got to have through spindle coolant with these insert drills. We'll toss 3 holes in there.
So one of the things we talked about was spindle load, and you say you feel comfortable running that all day long. It's always a balance, right, between tool life and how fast you're removing material?
Yeah, absolutely. So with regard to spindle load, so the vector drive and Haas machines will allow you to run below 150% continuously, right? All day long in that cut. At 150%, we can go continuous for about 30 minutes still before we are, run into trouble with maybe overheating the spindle motor.
Right.
And even if you bury this thing at 200% spindle load, you've still got about 3 minutes of cut time to get away with it. So there's still plenty of headroom utilizing the vector drive in our machines.
Right. But at some point, you're going to be compromising tool life, right?
Yes, absolutely. You don't want to push things too hard not because the machine can't take it,
Right.
because the tooling can't take it. The last thing you want, if you make parts for a living, the last thing you want is a catastrophic tool failure because you lose the tool, you lose the part, it's a mess.
Right.
And so reasonable spindle loads for your cut and your tooling, in my opinion, hover around 100, 125%. I wouldn't try to go too much more than that on a regular basis. Backing off of there is definitely going to give you longer tool life.
Right.
And it's not that it injures the machine or anything, it's more about the tooling.
That's right. Yeah, when I used to, in my previous role here, I used to go to a lot of customer shops, and guys would be running their machines at 30, 40% spindle load, thinking that was going to make them last longer.
Yeah,
And
yeah.
it probably did, but you're leaving money on the table.
Yeah,
when you're doing
for
that.
sure. You're sure. The extra time, cycle time that it takes to machine at those lower spindle loads is costing you money.
Exactly.
For sure. So I wanted to take a quick look. I'll show you the dprint file here that I created. So at the end of this program, I wrote the maximum spindle load recorded by each tool. So tool 1 had a maximum load of 151%. Tool 2, which was the 3/4 inch end mill, did 83% at a maximum. The drill was 111%, and our chamfer tool was only 5% spindle load. So you get an idea of where those loads came out, right? Well, 150 for the face mill, 83, 85 for the end mill, and then 111 for the drill. Now let's pull up the torque charts and see how that information jives.
Hey,
with
look,
what
I got
we
it
have.
right here for you. All right, I'm going to scoot over here just a little bit.
So when we were preparing here, I recorded 155% spindle load on that face mill the first time through. You can see that the maximum torque is up here at 90, and that's 200% spindle load. You can see we talk about that here. The values shown for horsepower and for torque are at 200% of the load of the spindle motor. So our cut was 155% of that spindle load. When I take 155 and divide it by 200, I get 0.775, 77.5%. That's my conversion factor. So at the RPM I was running, 10,082, I have right at 90 foot-pounds of torque. So 90 times 0.775 gives me 70 foot-pounds of torque. So that's the torque value that I pulled, 70 foot-pounds at 155% spindle load. Now let's pull up the next chart. This is the 3/4 inch end mill, and that was running at 2929 RPM, 2,929 RPM. So my torque value is a lot lower here because the chart has come down. So at this RPM, I have less available torque. I pulled a 84% spindle load and did the math on that, and that showed me that that end mill was requiring 35 foot-pounds of torque, and this is where that 35 foot-pounds falls in. Remember, this is my maximum, not that, when I'm making this calculation. And then the last tool.
So you actually, in this case, you had quite a bit. You have a huge headroom in terms of running that tool harder, but
Yes.
you probably don't want to run it that much harder.
Right. I would take, in that case, I was taking 250 thousandths width of cut and 1.5 times diameter deep. So I would ease that width of cut in if I needed to remove more stock per cut. That's how I would utilize the available spindle load that I have on that tool, and I'm probably not going to harm that tool or cut its life down at all by increasing that width of cut.
Right. When we were kind of preparing for this, you were talking about how one of the things you like to do is kind of start, if you're unsure about what spindle load you want to use, you'll come in and kind of start light,
Yeah.
and then see where that puts you, and then do the calculation.
Yeah, absolutely. So the way I would approach it if I was unsure about the cut I wanted to take, I would get the speed and feed information for the cutting tool and use that right in the middle of the speed and right in the middle of the feed rate information, and then go ahead and take a light depth of cut, right? Set up your cut with the width you want, but take a lighter depth. And then, for example, let's say you took that light depth of cut and you had a 50% spindle load. Well, if you change one cutting parameter, like depth of cut only, you can double that depth of cut and your spindle load is going to double. So you go from 50% spindle load up to 100, so you can take that, that cut twice. So you take twice the original cut. You're going to double the cut, it'll double the spindle load on you. So that's how taking a light cut, monitoring the spindle load and seeing how much available torque you've got or headroom you've got on spindle power, and then go from there as far as adjusting and optimizing your cutting parameters. But definitely go with the recommended speed and feed and adjust your cut parameters as far as depth or width of cut.
Right. It's just a practical, empirical way to quickly get to a good value without maybe doing some involved, power calculate or something. You just start off at the recommended values and change depth of cut.
There's also milling and turning calculators on the control where you can punch in your numbers and it'll give you a rough value for required power based on what material you choose on that calculator.
Right. Okay, so third tool.
The third tool here was the drill. We can see that was running at 1,650 RPM, where we're back up in our maximum torque range to see, but we pulled 110% spindle load, right? 110% divided by 200 gives me my percentage, which I multiplied by the 90% foot-pounds, and the percentage was 0.55 actually. So 55% of 90 foot-pounds of torque is 50 foot-pounds of torque. So that's what that cut pulled, and I was definitely right in the sweet spot for that tool at 100%, 110% spindle load.
Cool.
So that's how you kind of translate the spindle load numbers to the torque chart and figure it out.
Right, you have all that information on you know what your spindle load is from the machine. You have this information on the website or any other, any other place you're getting your tooling, and it's easy to get started.
Yeah.
Cool. Thank you, John.
All
I
right.
think that's it for this machine, right?
All right. We'll see you later.
We will see you later. Okay, so we're going to transition over to Bop Singh and Brian back over here on the ST30LY right across from me.
Yeah. Hey.
Hey, Brian.
Okay, so ST30LY, we're going to go from milling to turning. Talk a little bit about what you're making.
Okay, before I do, just to let you know, at Haas, all the lathes, about 80% of the time are running steel, so it's nothing new to us. We do it all the time over here, mix spindle shafts
Yeah,
and
so
lathe spindle shafts.
I guess I should have done what I did to John, talk about your background. You've been at Haas for how long?
20 years, 15 years as a machine shop supervisor.
Okay,
Yeah.
so you supervised the machine shop and you specialized in turning.
Exactly, yeah.
And so
Yeah.
if anybody knows how much steel we turn here at Haas, it's this guy.
Yeah, it's all steel for lathes, so.
Yep. Okay.
Okay, so we're running 4140. We're doing some simple turning, it's very simple. The blueprints come up on the screen.
Yeah, you want to look
Frank?
at want me to change over the first
Yeah.
tool? Or
Yeah, let's go to the first tool. Simple, on the top left, it's showing the tooling path, real simple. and we're using a CNMG 433 insert. Now, the most common roughing insert in the world is probably the CNMG 432. We're just going a bigger radius because I really want to push this insert, show it off. It's a HRH, which is a Haas roughing heavy insert, should I say. It might not be available yet online.
Yeah. So on the website, you know, the turning inserts and turning tools are just another page here on the Haas tooling part of the website. But yeah, so I have this is an example of a similar insert. I think it's going to be next week or something. That the ones you're using are going to be on there.
Well, if it fails now, we might not even go on. You never know. So we'll see. We'll see. Yeah, HRH. I'm really comfortable with it. It's awesome insert. We only just got it in, so that's why it's not released yet. So we're going to go with that and push this first tool. We've got 3 tools coming.
And
do you want to talk about the loads first, or you want to talk about them after?
Yeah, let's talk about, okay, so the depth of cut I'm going at, if you look at the top right graph, it shows the feed rate increasing. The bottom scale is the feed rate increasing left to right, and the depth of cut is increasing from bottom to top. The red ring shows that where I'm cutting this, and it's at the extreme end of this insert. So we're cutting.
You're definitely pushing this hard.
We're at 200 thou depth of cut, probably 18 thou feed, and the spindle speed recommended for 4140, which is an alloy steel. The bottom graph shows it's 630. We're actually going to go with a low carbon. We're going to go with 850. So we're pushing this beyond.
Yeah, you're pushing it really harder than
we're pushing it beyond.
You're supposed to, but
just to see some really good chunky chips, basically. So
Yep.
yeah.
All right. Let's do it.
So
let's do it.
Let's Sal, you want to come in here before he starts?
Yeah, before you press go, let's get in
make
close.
sure.
You've got that action cam, but I think Sal's shot's going to be the best here.
Yeah,
I
so
agree.
6 1/8 inch diameter material. It's, like I said, 4140. The spindle load you can see is at 165. So it really, you want to be at 120 to 140, then you could run all day. We're just pushing it a little bit more just for this demonstration. Sal, I don't know if you can close in on the actual insert, but it should be glowing red. That's the heat dissipating from the insert, and it's falling to the ground. So most of the energy is being absorbed by the chip or the swarf. I'd say 70% is the chip. I'd say 20% of the heat is going to the insert, and about 10% to the part. So. Real nice, real juicy cuts, nice popcorn sound coming out, so. Just doing the final profile. The last pass is coming. Okay, so Sal, that took less than just over 2 minutes. If you want to get out of the way, I'm going to open the door just to let Brian see. Now, if we open that up, there's a lot of heat there. But go ahead and touch the part. Trust me.
Are you setting me? Is this a setup?
Nice and cool.
It's nice and cool.
Nice and cool.
Yeah.
Most of the heat is down there on the insert. Material is kind of cool. So that's exactly what should happen. That's how it should go. So the next tool we're going to run is the DNMG. So Andrew, can you?
Yeah,
pull that
let's
up?
go to the next one here.
So the next tool we're going to do is going to rough the profile, and that's a DNMG 433. It's the same HRH insert we got for the CNMG. I'm just removing these.
Maybe we can give those away at the end of the
Get
year.
those out of the way, just for the demonstration. It's not
souvenir.
good.
If
Yeah.
it's a real trade show,
Yeah.
someone would want to take
People
those
would
home.
be lined up.
Cut their hands on the way out.
Yes.
Yeah, the reason I'm using the DNMG is because we're doing a 30 thou relief, and the DNMGs have got 32 degrees clearance, so we can plunge in there. We
So
can
you're
push
still
it again.
fully doing a roughing pass.
It's still
You just have better
roughing,
relief,
but I've
right?
backed it off a little bit because this is a 55-degree insert. So if you look at the graph on the top right, it is showing we're going about 160 thou depth of cut and 16 thou feed. The speed is actually above recommendation. It's at 850. So yeah, we're pushing this
You're
insert
pushing
as
this
well.
one about as hard as you did the first one, right?
Yeah, the load's going to be less. We are going a little bit less on the depth of cut, so the load should be less.
You want Sal to get in there?
Yes, Sal, come on
All
in.
right, let's get in here. It's what everybody wants to see.
Same thing, insert's glowing. First pass isn't as deep as the rest of them, so the next plunge you'll see the insert really working, really doing its job. So shall we go ahead and run the final pass, which is going to be the finished profile. So there it is, it's just relieved the little diameter there, so we can go in with a finish tool, which is going to be our VBMT, which is the third tool and the final tool. It's just going to do the profile. Now usually you use a V&MG, which is a negative tool, but because I'm doing a profile and it's going to go around a radius and use the back of the insert, I'm going with a VBMT for chip control. So
All right, let's do it.
Let's do it.
Come back in, Sal, making you go back and forth constantly.
door lock.
I can smell the steel.
Oh, the door's not locking. Hold on. I think we've put too many chips in there, mate.
You're not supposed to open it until the program's done, Bob.
Yeah. There we go. That's going 1200 RPM on the surface speed. Going around the profile, nice chips. Just going over the top, and that's it. Didn't touch the diameter, I think I changed my offset there, so, but not to worry. That's all done. Good finished part, and you can see that finish insert is a little bit warmer because the insert's not doing its job. It's not as hot as the roughers.
Okay.
So, but we can show you how
Those chips, they're
there's chips.
steaming.
Oh yeah, there's chunky chips right
How do I
there.
know they're hot, Bob?
Yeah, well, let's turn the coolant on. Let's see what goes on here.
Sal, you want to jump in here? You want to get this. This is how you know the chips are hot.
Now they're steaming. Now if I actually stop that and open the door a little bit, you'll hear if you stay there, Sal, you can hear them all sizzling and get in there. Good cheap, good inserts, good chips, all the heat's there where it should be.
That's a great demo.
Yeah.
Where's our mist extractor?
Yes. Cool. All right.
Yeah.
Thanks, Bob.
Okay, thank you.
Cool. So now we're going to move on and take a look at some of the tool testing data we covered before.
Yeah,
right?
that's right. So Bob's been in charge of testing for all the tools for HaasTooling.com on the turning side. John Nelson's done the milling side. So we're going to talk about, we got a presentation up so you can talk a little bit
Yeah.
about what your criteria was as you tested all these tools.
Yeah, pretty much all the information John was doing, I was capturing the same style for the lathe. So depth of cuts, the speeds and feeds, what material we were using, what was the spindle load, what was the material removal rate. All that information was gathered for a lot of inserts that are on the website right now with lots of different materials. We tested Stainless for the first time ever. That's the first time I've done that for a long time.
Yeah, because we don't cut very little stainless here.
Very little here. So stainless, cast iron, regular steel, high alloy steel, heat treat materials. We test a lot of inserts, and this is the data we came up with.
Yeah, so you have tons of data points, of course.
Oh, there's pages and pages of D-print information that gets put into the USB, and then we just load all that information and save it all for future. And then if you continue, and what kind of chips we were getting, we record that information as well.
Yeah, like in the case of this machine here, you were cutting like
Number
these
4,
Cs,
yeah,
right?
the Cs.
Fours?
That was good machinability, so you get nice C cuts. I like the number 2s and 3s. I like a bit of a.
Is that maybe because you're going a little bit extra hard
The
here?
material's got good machinability properties, so it did chip really well. And we were pushing it a little bit more than we should have been. And also, every insert, we would check the corners, we would check for cratering, for what kind of wear we were getting, what kind of finishes we were getting. We would save those chips. We've recorded all that information for most of those materials.
Yeah, so you're looking
yeah.
at a lot of these as they reach their failure point, it looks like.
Failure points, comparing inserts, finding out like that HRH was one of the best performing, and the one that's rated for steel was excellent on a stainless as well. So
yeah, you were saying earlier that particular HRH insert is just a really good
versatile insert, goes all over
across the board.
That'll
right?
help you with it. If you're doing lots of different materials, that's the insert to go with.
Cool. So then steel finishes. All right. Well, I guess that kind of wraps that up.
Yeah.
Thank you.
Thanks. That was an impressive demo.
Thank you so much, Bach.
I'm going to go just.
All right, so now we're going to jump over to
aisle.
the VF3YT50 over here.
Yep.
And Brian and John are going to resume.
Yep. So we're back with John. VF3YT50. This is a 50 taper.
Yeah.
A lot more. We've been talking about horsepower and torque. We've got more of both on this machine.
Yeah, absolutely. So this is the 50 taper high performance spindle on this machine. It's got a maximum peak of 60 horsepower, a 2-speed gearbox in it. All the 50 tapers have gearboxes, but this has the additional higher horsepower motor in it. Set up a very, very similar demo. Again, it's 4130 low alloy steel. And the cutting tools used in this demonstration, I'm basically using the same cutter that we had in that VF2, except this is the 4-inch version. So it's 1 inch larger on the diameter. And when you step up to the 4-inch, this is a 7-flute cutter. So we're using the same insert on that. I programmed the same surface footage, 850, as well as the same feed per tooth, which is 9 thou and 8 tenths. A hair under 10 thousandths feed per tooth. The second tool in this is going to be the 3-inch 90-degree shell mill. So this 3-inch version is a 6-flute cutter. It uses the same grade of inserts as that, obviously a different style. Those are the 45s, these are the 90s. But as far as surface footage and feed per tooth, exactly the same as that previous cutter, 850 SFM and just a hair under 10 thou feed per tooth. This cutter is going to go 3.325 deep, 325 thousandths deep. Okay. On this one with a 2-inch
How deep are you going on the
width.
face mill?
I'm sorry?
How deep are you going on the
The
face mill?
face mill is going to be 220 thousandths deep and 3-inch wide width of cut with the 4-inch cutter. So 3/4 of the width and 220 thousandths deep. The third cutter in this demonstration is the 1.5-inch insert drill. We're going to pop a couple of holes with that baby. Programmed at 600 surface feet and about 6.5 thou per revolution in that same steel. And then the last tool is a 45-degree chamfer mill. This is the 3-flute version, programmed at 800 surface feet and 7.5 thou feed per tooth.
Okay.
All right. I think we're ready to go. Why don't you hit cycle start over there?
You're going to let me
I
do
did
that?
this.
Do you
I
want
did.
to? So sorry, who are we going? Is Sal going to? Oh, you're going to come in, right, Tyler?
Get Tyler in here. You trust
Got
me
to get close for this.
Yeah,
one.
yeah. I think I can let an engineer push cycle start.
I can always blame you. You programmed it. All right, you ready to go, Tyler? All right, let's do it.
I did the same thing, recording the spindle load of each of these tools. Oh, you can see better than I. What do you have over there? On the spindle load.
right around 100%,
Yeah.
just under.
The next cutter coming up, the 3-inch 90-degree shell mill, is going to make a fair amount more noise than that. The 90-degree cutters always make more noise when
Yes.
cutting than the 45s, but you can see again those chips coming off straw colored and then turning blue in the pan. Sorry about that, folks.
One too many practice runs on that insert.
Yeah, didn't do that in any of our practice runs. Apologize for that. There's our 1.5 inch diameter drill.
And that spindle load is under 60%, so you could push that a little more
Yeah.
if you were so inclined.
Yeah, with this drill, I wouldn't increase the spindle speed as much as I would push the feed rate a little harder.
Okay.
There's our 3 holes, and then we'll come in with the chamfer tool and hit the sharp edges here.
Clean it all up. And of course, this is minimum spindle load,
Yeah,
taking
yeah.
almost no material.
Just taking the sharp edges off.
And I think what we'll do when this tool's finished, maybe we'll grab some chips. You've been talking about how they're straw colored when they come off the
Yeah.
tool, and then the color that you like to see at the end. Maybe I'll scoop some out of there and
Okay.
we'll get a close-up of them. This whole room's got that smell of steel. I love the smell of steel in the morning.
Yeah, there's definitely a unique odor when steel gets cut.
Yes. So what are the different, you did a video, as I mentioned, on the chamfer mills. What are the different angles that we have available?
Yeah, so on the chamfer tools we have they come in measured from center line, 15 degrees, 30 degrees. We have several different 45-degree versions and then a 60-degree version.
Okay, that's right. Okay, we can open the doors. Tyler can get a good shot of the finished part there and all the smoke. And you want to grab some chips?
Yeah, absolutely. Let's see.
And Tyler, maybe just hang out here and get a close-up of those chips.
So I can tell this is the chip that came off of the 3-inch 90-degree face mill. We've got nice commas coming off of there. That's a little bit hot. And then here's chips from that drill. Those were obviously easy to come by. Those came out really, really nice. Obviously they're not blue color because there was coolant, through spindle coolant being
Right.
used on those. We got really good chip breakage here. These things were cutting right, just perfect.
Nice. Okay, and then once again, the way you program these, you want to go through the torque charts real quickly?
Yeah. Let me bring up real fast that the recorded.
You can come out, Tyler.
Here were the recorded spindle loads of that cutter. So we took that 4-inch face mill that was going 220 thousandths deep and 3 inches width of cut, and we pulled 116% as a maximum spindle load while that tool was in the cut. The second cutter, the 3-inch 90 degree, did 96% spindle load, and then that drill pulled 78% spindle load.
Okay.
Again, we did the torque charts for this particular machine, and you can see here, again, it's a little bit busy, but we're really paying attention to the torque in low gear. None of the tools ran above the just under 3,000 RPM is the shift point. So all these tools ran in low gear, and that was 200% spindle load, right? Our cut here running at 812 RPM, so I gotta find the right RPM. And again, my percentage was 116%. When I made this chart, it was 113%. So I took the 113% spindle load, divided it by 200, the maximum available, and got a conversion factor, and then multiplied that by the amount of torque at 812 RPM, and that gives me the calculation of 210 foot-pounds of torque that tool pulled.
Okay.
And you can see, again, just over 110% on the spindle, 113%.
then
The
the
next
3-inch?
tool, sorry, go ahead.
Go ahead. No, the 3-inch mill?
The 3-inch shell mill ran at 1,082 RPM, so that's why our line is over here at that RPM. And you can see our torque is dropping pretty dramatically right there. So I'm somewhere in the 290, 280 foot-pounds of torque at that RPM, and my spindle load ended up being 149 foot-pounds for that tool, and that again came in right at the 100%, 99% spindle load.
Right.
So I was at half of the available maximum torque at that RPM. And then the last tool, which is the 1.5-inch drill, was running at 1,528 RPM. Now we have quite a bit less torque down there. We're down about 200 foot-pounds for this calculation. And again, the 80% spindle load divided by 200 possible percent spindle load is giving me a conversion factor that I multiply by the torque at that RPM, and I ended up pulling about 80 foot-pounds of torque with that tool.
Great. Okay. I
All
think
right.
that's going to just about wrap it up.
Yeah.
I'm going to come in here. We'll wrap it up with John. I think one of the things that we the three of us talked about yesterday, we kind of had fun with it, of some of the people on YouTube who like to post comments of they've got a Haas machine and they can't cut steel. We have the contingency in place to help those people.
Yeah, absolutely. It's not even not so much comments on YouTube as it is like the blogs that machinists blog sites where people go on a blog site and ask a question about their Haas machine, and I read this and I see that somebody's responded to it and they're not a Haas customer either, but on their machine this, and they're giving them advice, and I'm thinking to myself, why doesn't this person just contact their local Haas factory outlet or the Haas factory to get expert advice about that machine? We're the ones who run these machines all day long. We know most about these machines. Don't ask somebody on the internet that you don't even know who may or may not be giving you information, good information, on purpose. They might be leading you down the wrong. Who knows what's going on the internet?
Who knows? Yep.
It's really important that you contact us because we're here to help you. Again, I've always said that at Haas Automation, customer service, we consider ourselves a world-class customer service organization. We're here to help our customers get the most out of their machine tools.
I think that's a great conclusion. I don't have
I
anything
couldn't have said
to
it better
add to that.
myself.
Well,
Yeah.
we want to thank all you for watching. Thank you for the comments. We're going to be back with you doing some more Demo Day Lives in 2021. Not sure
right.
exactly
Yeah, we don't know what
that's
the
going to
cadence
look like.
is, but,
Yep.
but we'll surely be back because I think we'll all be in the same place at the
Exactly.
beginning of next year.
So thank you all for watching.
Thank you so
and
much for
thanks.
joining us.
See you in 2021.